Want to trade? All right, so we're going to take a look at our data. I'm going to have to transfer it over between the computer and the laptop. Here's the dice rolling that we did, and we're going to take a look at one distribution in statistics. There's lots, but the goal when we model stuff is to come up with a good model, something that we can predict things with. And the one that we're looking at here is fairly close to the normal distribution that you're going to learn about. So if we would have rolled the dice more and more and more and more, meaning we got more data, I don't know, we probably had about, I'll guess maybe 100 or 200 different rolls. But the more we roll the dice, the more it would come out to look like the distribution for the normal distribution. So that's one thing you got to know about statistics. They're not perfect, just like the casino. For example, you'd be doing yourself a terrible business if you went into the casino and you only ran your casino off one bet every night, because that could make or break your casino in one bet, right? That's why there's lots of different games, lots of different people, all different kind of things going on. Because you know, that means over many people gambling, you're going to come out ahead, but you may win or lose on an individual one. Same thing with like these distributions we're going to look at. Someone might tell you, well, the life expectancy in Canada is 85 years, you know, and that's the normal age, but you might live to be 90. Someone else might live to be 60. But overall, you know, it's going to form that kind of a shape when we look at the chart. So, the first thing, I'll switch us back to our notes. The first thing we need to talk about is just the shape of it. Maybe I'll zoom out a little here because it's... Okay, so here's a few for you to take a look at. Now, the normal distribution is sometimes called a bell curve, and you can actually see it. I included it on purpose in the bottom left corner there. That would be what we consider a perfect bell curve. So what do you think? If this is the data you gathered, which one of these up here, or maybe ones, would you say makes sense to call a normal distribution? You can just say top left, top right, bottom left, bottom right. What do you think looks like the bell curve? It's the little blue line in the bottom left. Bottom right. Hands up if you think bottom right makes sense to be normal distribution. Okay, so you're still learning about it, but yes, that's actually, I believe that is the heights of over 6,000 Americans that they recorded data on. So that's the height curve for maybe adult males. But it turns out to be this, again, this nice sort of bell-looking shape. What do you think? What else up there might have a normal distribution? Bottom left? Well, ignore the blue line then. The blue line is just to compare the normal distribution, the bars of the data. So look at the bars. Which one do you think up there might also be a, sure, Joe? Top left? Yeah, top left, again, it's not perfect, but it's not bad. It would also fit under that category of being a normal curve. So one thing you're going to want to get when you're looking for the normal curve is you're looking for that bell shape, but you're looking for most of the values are in the middle, right? Like, I mean, I'm average height. I'm like about 5'9", so I'm right in the middle. There are people taller than me, and there are people shorter than me, but the further away you get, the less and less of them there are. That's what the bell curve looks like. The further away you go from the middle, the less and less people there are that have that trait. So that's the first skill you need to be able to do today, believe it or not, is can you identify which one's a normal curve? Okay. Now, for our graph, you can just take a look at it. I know I mentioned this at the beginning, but if we rolled enough again, you'll see the data. There's a lot more 6, 7, and 8s than anything else because they're the middle of all the rolls. So, you know, it's not a bad trial that we did for rolling dice, but that's what we would consider, yeah, that one probably fits into a normal curve. So here's the most important part that we got to start with today. So for your notes, everybody needs a copy of this. So I'm going to let you guys take a minute just to copy this out. It is a picture of the normal curve, and you can copy it down. I'll explain it to you in a minute once you have a picture to look at. Okay, so what this chart represents, we're going to refer to now as the 60 8, 95, 97 rule. Yeah, 99.7 rule. So when you hear me say that, this is the picture we're thinking about in your head, and I'll tell you what the rule means. But the first thing we need to say is what these things at the bottom are. Now, your textbook is using what standard math textbooks have used for a long time. We're going to just use the English words for them. So when you guys have a test with me or something like that, you'll get the actual names for it. But that funny looking U is actually a mu, and it's the average. That's just the letter that they use, the Greek letter for average. So I suppose if you're doing math in Greece, you know exactly what it means. The number underneath it is sigma, the Greek letter S. And what do you think it would stand for? What else have you done? Think about it. Standard deviation, right? So that's what that sigma, that funny looking circle with the line on top, that means standard deviation. Oops. So I'm going to explain to you what this rule means. And the nice thing about a normal distribution is they can take a lot of different curves. But the property here, this rule is always the same. So for example, if we measured the average height at Johnson Heights, and we took the standard deviation, we could plot a normal curve. But then if we were to go up the street to, say, Fraser Heights, we might find that it's a different average and a different standard deviation. So we'd end up with a different curve, but this rule will still be the same between our schools. So here's what the rule says. If you're here at the average, so I'll put this in the middle, this is everybody within one standard deviation. So what it means is everybody that we've just measured, 68% will be within one standard deviation. Right? So I'll show you how you can apply this to using this for actual real stuff. But that's what it says, is if you're one standard deviation from the average, that'll be 68% of the population. So what do you think? If I'm 2 standard deviations, how much of the population do you think I will see? Make a wild guess. 95. If I'm 3 standard deviations, how much of the population do you think I'll... 99.7. Yeah, 99.7. So there might be a question that say something like, here's your average, it's 10, and your standard deviation is 2. What percentage of the population would be from 8 to 12? That's 1 standard deviation higher, 1 standard deviation lower, so 64% will be in there. Okay, so I'll write it down for you here. That's 68% of the population are within 1 standard deviation. Of the average. And we can repeat this. 95% are within 2 standard deviations. And almost everybody is within 3 standard deviations. So if you wonder why mathematicians try to make life harder by using all those symbols, they're actually probably the laziest group that you'll meet because they're always trying to shorthand things. When I was in university, you could write whole sentences without actually doing any meaningful words or anything, just a bunch of symbols and gibberish together. They even, back in the old days, when all they had was printing presses, so we're talking like 16th, 17th century, they actually went to the pressman and said, look, we're really lazy and we don't want to be writing this out all the time, like big words like standard deviation. And they said, how can you help us? And they said, well, we only have an alphabet to work with, but we can flip them around and upside down and stuff like that. So for example, what does that look like to you? An upside down A, that's shorthand for every or for all. So there's a whole bunch of different weird symbols they threw in there just because they're so lazy. And rather than writing standard deviation out, you can also write that. I'll know what you mean. The sigma. Okay, so here's an example for you. A shoe store is opening up and wants to have shoe sizes for 95% of the people that come into their store. If the average shoe size is 9 and the standard deviation of the data they gathered was 3, what shoe size should they order for their store? Right? Like, you don't want to be a business that's turning business away because you don't have enough sizes, but at the same time, it's probably not a good use of your money to stock size 35 shoes. Right? I mean, we don't even have a basketball team anymore in Vancouver, so I don't know how often that comes up. Yeah, I used to have the Grizzlies, but now, where are they now? That's Memphis, right, Memphis. So, 95% of the people, if you look at our 68, 95, 99.7 rule, how far are 95% of the people from the average? Within 2. Yeah, so for us, that means what we're thinking is 95% are within 2 standard deviations, and for us, a standard deviation was 3. So we could say 95% are within 6 shoe sizes, because that's 2 times the standard deviation of 3 of size 9. So the sizes we'd carry, I'm going to write it like this. It's going to be a 6, it's going to be a 3, to a 15. If we carried shoe sizes from 3 to 15, we know that our customers would have 95% of them we'd be able to do business with. 5% we can't, but I'm sure, anybody know people with oversized 15 shoe? Yeah, usually you got to go to a specialty store anyways, but these are how you can make those decisions in the real world, is you know that you got to make some sort of population. This is one quick and easy way to do it with standard deviation. So, a manufacturer offers a warranty on its coffee makers. The coffee makers have an average lifespan of 4.5 years. And if we looked at their, when the coffee maker stops working, there's a standard deviation of 0.7 years. So, how long should they offer the warranty if they don't want to repair any more than 2.5%? So, we have to think a little harder here. How do we use this rule? And I'm going to go back up to the table to show you. So what we're interested in is 2.5. So here's how you find it. Actually, does anybody think that, which of those 3 numbers do you think we're going to end up using? 68. Yeah, it's tough if you've never done it before. Well, you're looking for the end of your warranty. So what we're going to do is, we're going to say, if I have 95% of the population, how much is left over here? On the outside, how much is left over if 95 is in the middle? 5, right? If you're giving the warranty, and this side here, maybe this is like 2 years or something like that, and maybe this side is like 6 years. Which side is it that you want as the manufacturer? 2. Well, if you did it at 2 years, you'd be excluding everybody on the other side, which is like most of your customers, right? So, what's that?
We're cheap.
You're cheap, okay. Well, let's think about it then. Should we use the left side or the right side? Let's choose all 3. Well, someone's got to make a decision, right? Because if we're going to slap a warranty on that box, we have to honor it. So think about it. What's the safest way to pick your warranty? Is it going to be the top half or the bottom half?
As a consumer or as a...
As the manufacturer, right?
2 years.
Well, then 2 years.
Then 2 years, the bottom half, right? So that's, when you're doing that, you gotta use a little common sense, right, to think of which side you want. But other than asking you for the entire 95, 68, or 99.7, you might have to think of which half you want. So for us, as the manufacturer, we're gonna end our warranty on the bottom half there. So, whoops. Let's figure out where that is. Okay, so if I have 4.5 minus 2 standard deviations, and what that looks like is, here's 4.5, the average lifespan of my coffee maker, and I've just marched it 2 standard deviations over to 3.1 years, and that means just a second here. Let me get a picture so I can explain it a little better. So what we're looking at then is we've got an average life of 4.5, and if we took 95%, that means it'd be from 3.1 to 5.9 years, because that's 2 standard deviations from the average. Okay? 95 means this other area that I'll draw in purple. Together, the purple equals 5%, because together they make up everyone. So I got 5% if I took both purples, but I only want 2.5, so I'll take this 2.5%. Okay? So that's what we have here is 3.1 years is where we want to stop the warranty. Otherwise, we may need to pay out for more coffee makers. Okay. So again, we'll talk lots about it in tutorial, because I know there's some questions out there. Does anybody want to throw a question up right now? What's the... that's when we meet when we're not in the theater. In small groups, 20 at a time. Yeah, friends? It's the same one we're in right now, 5. Okay, so I think there's one more here that we'll try before we leave it at that for the day. Okay, so let's walk through it together. You have 130 bottlenose dolphins, and it says they live about 39 years on average. The standard deviation is 3.5 years. So how many of them do you expect to live past 46 years? Okay. So first of all, we have to figure out how many standard deviations is 46 from 39. So this is our curve. We'd be looking at something like this. And this would be the average age of 39. And I'm out here at 46. So what I want to know is, how far did I have to move to get there? Okay, so let's just think about it in years. How many years did I have to move to get there? 7 years. But when we deal with the normal distribution, we're always interested in average and standard deviation. So change it from 7 years to something that's going to help us solve this problem. Yes? 2 standard deviations. So that means I moved over 7 years, or 2 standard deviations. Okay. So what it wants to know is how many of them will live more than 46 years. So here's who we're looking for. These dolphins that would live, there's not many of them, but that top half, how many are going to be in there? So we need to take a look at our rule again. if we're 2 standard deviations away, how much space have I used to get there?
Why are we 2 standard deviations away?
Yeah, how do we find that out?
Sorry, I'll highlight it for you. Right there, it's standard deviation is 3.5, and we move 7 years. The average is 39.
Here we go.
Average is 39. We're looking at 46. So that distance is 2 standard
There
deviations.
we go. I got
Okay.
it. Makes sense.
So what portion of the population are there right now in this black area of the chart here? 95% are in the middle there. So how many does that leave in the green area? 2.5. Yeah, 5% is left over in total. But because we're just dealing with one of the halves, right, this would be the other side. So 5% in green, which means this has 2.5 of it, and this has 2.5. Okay. So we'll talk more about the 68, 95, 99.7 rule when we get to your tutorials, but that's where we're going to stop the normal distribution for now. Okay?